In this video, we're going to prove an important property of the algebraic elements of a field extension. But first, I want to raise a question. In a previous video, we proved that every finite extension is algebraic. We proved that. So one question you might ask is the converse true? So what about the converse? Is every algebraic extension of a field finite? We're going to answer that question in this video. But first, just to set the stage, let's let F be a field. And let E be an extension of F. And we're not committing to E being finite or algebraic or anything in particular, just that it's an extension field of F. So what I want to do here is define H to be the set of elements of E that are algebraic over F. And we're going to prove that H is a field. Okay. At first we don't know that. We just know that H is a subset of E, which is a field, but we don't know that H has any closure properties, that it has multiplicative inverses, or anything like that. But we will prove that in this video, that H is a field, and it's a subfield of E, and it's also an extension of F. Okay, so just to draw a picture here, get our bearings, here's what we're looking at. Here's our base field, and then we have some extension of F, that's E, maybe quite large, maybe of infinite degree over F, and then we have this thing in the middle that consists of all of the algebraic elements of E over F. I claim that's a field, and it sits between F and E. Okay, it definitely has to be a subset of E. That's how we're defining it. But how do we know it contains F? So that's the first question. Why does H contain F? And you might pause the video and think about that and see if you can answer the question yourself. I'll answer it here. If A belongs to F, then certainly A belongs to E because E is an extension of F, and A is a root of the polynomial x minus A, which is in F adjoint X. So A is definitely algebraic over F. So in other words, everything in F is algebraic over F. So that's good. All right, but number two, how do we know it's a field? How do we know it's a subfield of E? All right, so to show it's a field, we're just going to prove that it has all of the necessary closure properties. So first of all, why does H contain the most basic things that it has to have in order to be a field? So 0 and 1. Okay, well that actually has been answered by question number 1. That's because these are elements of F. Well, these are elements of F. So just see question 1. Okay, so we already know that 0 and 1 are algebraic because we proved that all elements of F are algebraic. Now one little nitpick that you might make here is, well, how do we know that 0 and 1 as elements of the extension field are the same as the 0 and 1 in F? And well, the reason that that's true is because we already know that there are elements 0 and 1 belonging to F itself. Those have to belong to E because F is a subset of E. So if E has some other exotic elements, which we also might call 0 and 1, that is other elements that act as additive and multiplicative identities, maybe over here, well, you can use the same uniqueness argument that we've used for all of abstract algebra to prove that those actually have to be the same element. You can't have two different additive identities in a field. You can't have two different multiplicative identities. So these really are the same elements of F that we've been talking about, and we've already proven that elements of F are algebraic over F. Okay, so that was just a warm-up. Now let's ask a real question. Okay, why does H contain additive and multiplicative inverses of its elements? With multiplicative inverses, as usual, we're assuming that the element is non-zero. Okay, so first of all, suppose A belongs to H. Okay, so A is an element of E, and A is algebraic over F, which means A has a minimal polynomial over F. So let's use that. Let's call it f of x, and let's actually give the coefficients names. Let's call them, let's use c's since we're already using a for something else. C0, C1x, etc. up to Cn x to the n. Okay, so this is a polynomial having the property that f of a equals 0. That's what it means to be the minimal polynomial, is that it has a as a root and it's of the smallest possible degree. Okay, so a has a minimal polynomial. We're going to use that to get polynomials having negative a and a inverse as roots. We're assuming, of course, that a is not equal to 0 for the second part. Okay, so we know that C0 plus C1a plus C2a squared, etc., up through Cn a to the n, that's equal to 0. So how am I going to get a polynomial having negative a as a root? Well, I could do that by just creatively manipulating these terms and rewrite them as C0 plus, okay, and then I really would like to put a negative a here, but I can't just put a negative a without changing something. So I'm going to change the C1 to negative C1. There we go. And then I want a negative a here as well. And I can do that without changing anything because I'm squaring that. So I've got a C2 here. And then let's just write down one more term. If I want a negative a cubed here, then I'm going to need to change that C3 to a negative C3 in order to make sure that term remains the same as what it was before. And this last one's a little bit tricky because I don't know whether n is even or odd. So I'm just going to say that's negative 1 to the n, Cn, times negative a to the n. And that all still equals 0 because I haven't changed the value of any term here. I've just rewritten some of these using a gratuitous number of negative signs. All right, so now what I have is, so C0 minus C1x plus C2x squared minus C3x cubed, etc., up through negative 1 to the n, Cn x to the n. This is a polynomial still in f adjoint x having negative a as a root. So negative a is algebraic over f. Cool. All right, so that establishes that H contains its additive inverses. Now what about multiplicative inverses? Well, assuming that A is non-zero, I would like to go ahead and use this polynomial again, this f of x, my minimal polynomial for A. I would like to use this, or this identity right here rather, to get a polynomial having 1 over A, or A inverse, as a root. Now to do that, you might want to pause the video and see if you can come up with a way to do it yourself. I have an idea, but it's kind of cute. So the cute idea is we can multiply equation star, which is right here, all the way through by a to the minus n. That's a inverse to the nth power. Well, that gives me C0 a inverse to the n plus C1, and then I'm going to cancel out that a with my n copies of a inverse, and I'm going to have n minus 1 copies left over. I'm going to keep going like this and end up with Cn, and then my a to the n is canceled out by these n copies of a inverse, and that all equals 0. So this polynomial, C0 x to the n, sorry, I just think this is the coolest thing. Like, this is the sickest thing ever. cn minus 1x plus cn. So I just take that polynomial and turn it around, like turn the coefficients around. This is a polynomial in f adjoint x, and it has a inverse as a root. Now to do that, I did need to use a inverse, which meant that I needed to assume that a was non-zero here. But if a is 0, we're not going to be looking for its inverse in h anyway. So this shows that h is closed under taking additive and multiplicative inverses. So that's great. So I think that the main thing remaining that I need to show is that h is closed under addition and multiplication. So let's move this over, and let's start one more part of the argument down here, over on the right. Okay, so 4. Why is h closed under addition and multiplication? Okay, for this, I'm going to use something a little bit different. I'm going to take a much higher tech approach here, meaning that I'm going to use theorems that we've already proven pretty recently. Like number 3 was like banging this, or part of this theorem with a rock, meaning that I used just what I know about polynomials and tinkered using algebra. Like I tinkered here, and I did some tinkering here, and I managed to manually get polynomials having negative a and a inverses roots. All right, cool. But sometimes you want to do more than tinker. Sometimes you want to use the full power of the subject you're developing, and that's what we're going to do here. All right, so let's suppose a and b both belong to h. We will show a plus b is algebraic. So we're assuming that a and b are algebraic. We're going to prove that a plus b is algebraic, and a times b is algebraic. And that's what we need to show, because we already know that a and b belong to E and are algebraic over F. And because E is an extension field, we already know that a plus b and a times b already both belong to E. All right, so that part's known. We don't have to fret about that part, but we do need to show these are both algebraic. All right, so the way that we're going to do that is we're going to restrict our attention for just a little bit. All right, so consider the field F adjoin A. This is a finite extension of F of degree m, where m is the degree of the minimal polynomial for A over F. All right, so now I'm going to consider F adjoin A and B. Okay, this is a finite extension, or at least I claim this is a finite extension of F adjoin A. But now I have to be a little bit careful what claims I make, because whatever the minimal polynomial is for B over F, that may not be the same as the minimal polynomial for B over F adjoin A. I mean, for all we know, B belongs to F adjoin A, in which case the minimal polynomial for B over F adjoin A would be just 1. But we do know that the degree of this extension, F adjoin A and B over F adjoin A, won't be any more than the degree of B over F, with degree less than or equal to the degree of B over F. In other words, the degree of the minimal polynomial of B over F. Okay, so let's call the degree of F adjoin A and B over F adjoin A, let's call that N. Okay, so where are we going with all of this? Well, here's a picture of the reasoning I want to do. This was F, this was E, and somewhere around here was H. Now what I'm doing is I'm looking at very specific field extensions. So I'm looking at F adjoin A So A is somewhere out here, and then maybe B is outside of that. We don't really know whether B is outside of f adjoint A or inside of it. We'll just assume outside. So this is f adjoint A and B. Okay. Now one thing that we know that the degree of f adjoint A and B over f, that is equal to the product of the degree of f adjoint A and B over f adjoint A times the degree of f adjoint A over f. And that's actually something that we've proven, that if we have two field extensions, two finite field extensions, and they have degrees m and n respectively, then the degree of the big extension over the base field is n times m. So this is a finite field extension of f, which means it's algebraic. Okay, and wouldn't you know it, one element of that field is A plus B, because this field contains both A and B. It's closed under addition, so it must contain A plus B. Another element, for that matter, is A times B. So that means that both A plus B and A times B, because they belong to an algebraic field extension of f, that means these are both algebraic. Awesome. Okay, and let me just say one thing which might infuriate you. I actually could have used that same reasoning on these other parts here. I could have used these on negative A and A inverse, because both of those are also elements of, in fact, I could have used simpler reasoning. They're both elements of f adjoint A. F adjoint A is a field, and every element of that field is algebraic. So I could have used that to more easily dispatch this part, but I just love the idea that you can take a polynomial that has A as a root and manufacture ones that have negative A and A inverse as roots. I couldn't deny you that, so I had to do the harder version of the argument. But know that there is an easier version that you can do. And now that we've proven closure properties, we've proven inverses exist, we've proven H has 0 and 1, that means that we know, this is a field. Nailed it. H is a field. All right. So one more thing I wanted to get into this video. I know this is a little bit long already, but one more point, and that's about the question I asked at the beginning of the video. The question was, is every algebraic extension of a field finite? Okay, well, consider the field of real numbers as an extension of the rationals, and let, I don't know if there's an official name for this, I'm going to call it boldface A. Let A be the field of algebraic real numbers. And by algebraic, I mean algebraic over Q. Okay? Now I claim that this field, first of all, it is a field. That's what we just proved. That follows from the result we just established, so that this set actually is a subfield of the real numbers. But I claim that it is not at all of finite degree over Q. And I'll prove it to you. Suppose there were a finite degree. And suppose that degree was equal to, let's say, k. I'm going to show that can't be right. Consider the polynomial p of x equals x to the k plus 1 minus 2. That's irreducible by Eisenstein's criterion. And the extension q adjoin a root of this polynomial, let's just say the k plus 1th root of 2, that's a k plus 1 there, this has degree over q equal to k plus 1, which is greater than k. But this number here, the k plus 1th root of 2, that definitely belongs to A. That's an algebraic real number right there, which means I've got this field extension, which ought to be a subfield of the algebraic real numbers, but its degree over q is bigger than what I said the degree of A over q was, bigger than k. So that leads us to a contradiction. We can't have a subfield of higher degree than the field that we're coming from. So that shows that the field of algebraic real numbers, it is an infinite extension, but it's totally algebraic. It's the field of algebraic numbers. Everything in there is algebraic. So, moral of the story, every finite field extension is algebraic, but not the other way around. Not every algebraic extension is finite.